Hey everyone, this is the next video in the memory management series, and the topic for today is memory partitioning. Okay, so the topics covered in this video, you can check them out in the description, so you can find them, and there will be many more videos after this covering the further topics in memory management. So it's better to check out the topics you are looking for. Okay, so let's begin. So as we all know, memory management is done by the OS, in which it swaps processes in and out of the memory and manages the currently running processes. So in the multiprogramming environment, there is a term known as virtual memory, and it's basically implemented in paging and segmentation. So paging and segmentation are the main techniques used in memory management. But before we move on to those topics, which will be done in the future videos, this paging and segmentation, we first need to understand some basic techniques before that, some basic approaches before that. So we will be able to explain and handle how this paging and segmentation works better. So the first thing we can think about is how the memory should be organized is fixed partitioning. That is the memory to be divided in fixed partition blocks. Let's say like 8 megabytes of block. Okay, so when a program is loaded, it can be put into that block, and so it gets a fixed size that 8 megabytes. And when all the blocks in the main memory are filled, the OS can swap some blocks with another process it is trying to load. Okay, so in fixed partitioning, the blocks are of fixed size. Then this raises two concerns. That is, see, we have defined the size, but it's not necessary that the program will be less than that size. So yeah, the program can be big. So what the user supposed to do? User no, the OS handles this. So if the program is big, so the whole program can't be in the block at the same time. So it needs to perform swapping and overlaying, that is only the some portion of the program is at a time in the main memory. Okay, so if your program is too big, only the portion currently executed will be in the main memory, and the later on portion will be swapped inside when it is required. So that's for when the size is too big. Okay, but what say if it is small? So when it is small, it creates internal fragmentation. You may have heard this term fragmentation. So there are two types, that is external fragmentation and internal fragmentation. So what's that? See, the situation in which the space is wasted and it is inside the partition. That's, let's say, the occupied size is less than the partition size. See, let's look at the example, like say the partition is of 8 megabytes and the program is of 2 megabytes, but we are still allocating a, a program to a single partition. So the whole 8 megabytes will be allocated to that program, and the 6 megabytes inside of that will go wasted. So that's what we call internal fragmentation. So the the problem, this problem, that is internal fragmentation, and the one before that, that is if the program is too big than the size of the partition, both of these can be solved using, yeah, we can simply think that solved using unequal partitioning. So now we come to the topic of dynamic partitioning. Dynamic is at that time, at that instant. Okay. So in this, partitions are not of fixed size, are of variable length, and they're when they are brought into memory, they are giving the amount of size, that is the amount of memory they require. And so when still and the memory eventually get fills, and when a new program is brought in and it's not having the required amount of free memory, so some program need to be swapped out of memory, and then this program is brought in. Okay. So the size is variable, programs are swapped also in this. And so yeah, now in fixed site there was internal fragmentation. The problem in this one is there is external fragmentation. Okay. So okay, this is external fragmentation, not defragmentation. It's technique to solve this. Okay. So ignore this. This is external fragmentation. Okay. In this, internal was inside the partition and this is outside the partition, because see, many variable length programs are swapped in and out, so there will be some spaces which will be left later on, which when combined with other left spaces is big, but as a whole continuous space it is small. Okay. Let's see with this example. Let's say this part of the memory is taken by the operating system and this is the remaining free memory. So process 1 comes and it occupies this 20 of space. Then again process 2 comes, it occupies this 14 so combinedly 34. Then again process 3 comes, so the remaining space is 4 MB. Now the process 2 has terminated and it is removed from the memory. Okay, now there is another process 4 comes which occupies this space. Okay, so yeah, it fit perfectly. Then process 1 gets terminated and is removed from the main memory. Now process 1 is removed, process 2 is brought back in again and occupies this part. So as you can see, what happened here is the sizes of the various processes were different, and so there are some holes left in the memory. Yeah, these are called holes. Okay. So let's say there is some another process. Okay, maybe of, let's say, which requires 13 of space, but in the main memory there is 13 of space is not available. So well, but it is actually available, as we can see that this 6 plus 6 plus 4. Okay, it is how much? 16. Yeah. So 16 of space is still available, and our new program, which is, let's say, is of 13 but we still can't load it because this space is not continuous, so the program can't be loaded. So this thing is called external fragmentation, the fragmentation outside of partitions. Okay. So the technique to solve this is compaction. Okay. What happens in compaction, as compaction is the same as defragmentation. You must have performed sometimes as a defragmentation task as your management program, that is some system care program, notifies you that your disk is highly fragmented, you need to defragment it. There is function in Windows of defragmentation and in others also. So yeah, compaction is defragmentation, that is removing the fragments and shifting the memory to one part so that there will be continuous free space and your system will work faster. Okay. So yeah, in this OS shift the processes to get a continuous block of memory. And but yeah, problem is that compaction is time consuming and this wastes processor's time. So we can't be performing compaction again and again. See, we need to perform this to get free space here. So compaction is done, this will shift here and this process will shift above and there will be enough free space for the newcomer. Okay. So yeah, this wastes a whole of time, lots of time, as the various memory references needs to be managed in this. Okay. So to counter the fact and we can't use compaction, so there are many techniques, that is placement algorithms, how this placement should be done. So the many placement algorithms, the first one is best fit, that is it chooses the block closest to the size required. So let's say the size of the process is 12 MB, it chooses the block size which is equal to or greater than this. Okay, the closest one, best fit. See, these are the empty blocks, say 14 MB. So a 12 MB program, the best fit will choose this. Okay. The next one is first fit, and what happens in this is the program scans from the top of the memory, and the first one it is able to fit, so it provide allocates that process to that memory block. And the next fit is same as the first fit, but the scanning starts from the point where the previous allocation was done. Okay. So yeah, say this is our currently state of the memory, this is our current state. Okay, there are some free spaces and the last allocated block was this. Okay, so now we look at the first fit, and the first fit finds the space here. From the top it's looking and it finds the first space it can fit into, so the process is fitted here. Okay, the first free space it can fit into, that's first fit. Okay, now what best fit does is the closest it can do. Okay, so I think the program here is of 16M, and so it can fit in this 18M block with just leaving 2M of memory. So this is best fit. Okay, first fit here, there's 6 MB remaining, but the best fit fits it with the equal or just greater than that size. And now the next fit, see, this is the last allocated block, so next fit starts scanning after that. First fit started scanning from the start, next fit starts from the last allocated block. So the next fit starts the scan from here. Okay, so it finds free space here for that 16 MB program, so it gets fits here. So this is how these three algorithms, that is these three placement algorithms work. Okay, so as per the simplicity you can think, right, that the first fit is the fastest, and it is, you may not believe, that the best among these, as large amount of continuous free block is available at the end, which means that the first fit starts searching for the memory from the start, and there is a large amount of free memory left in the last of the memory, so big programs can also be fit later. So yeah, first fit is the best, and it leaves a large continuous free memory block at the end. The next fit create partitioning in the whole memory. The next fit will travel the whole memory here, then starts again, and it will create many small partitions in between. So the best fit is not so best, and it is the worst performer in this, because what happens with best fit, it leaves very small memory holes which are too small for any other process to utilize. And so yeah, there will be, if we implemented the best fit every time, there will be these small blocks, lots of them, and they won't be of any use later on. So yeah, best fit is the worst. There's another technique to partition is the buddy system. So what happens in the buddy system is, say you have some amount, that you have a memory block, which is your whole memory, and then there is a process which requires some amount of space. So if the process, so the process, how the process is fitted in this is the memory block divides into half, and repeatedly it partitions it into half, 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 until the partition is just equal or a little greater than required by the process. Okay, so okay, and let's say, see, this is the 1 MB block, and there is some process which requires, say, 128K of memory. So this block is partitioned into half, that is 502 and 502. Then it, the request is of 100K. So still this is more than enough. So it again partitions into half. Now that is divided into 128 and 128. Now this 100K is allocated this block. Okay. It can't be partitioned again, otherwise it will be smaller than 100K. Okay. So now another request comes which is of 240K, and it can be easily fit into this block which is of 256K. And another request is 64K. So this is a free block of 128K. So yeah, we can easily partition it and still get the exact size. Okay. So we get 64K. Now 256K, yeah, we partition this 512 and we get 256K. Now we are releasing B. Okay, we can say the B process terminated. So this is now unallocated. Now we release A. A is released here. Now request of 75K comes. Okay. So we again allocate this block which is greater than 75, and yeah, we can't allocate in this, so the minimum would be 128 to allocate this block. Now we release C. Where is our C? Yeah. So when C is released, so when a pair of holes become unallocated, they combine again and form a large block again. So yeah, when C is released, so these two become unallocated and they combine back to form a big large block, that is 128K. Now E is released. Where was he? This E released, so these two combine, and now then these two combine. Okay, so we get this 512 memory block, and when we release this also, so we get the whole block back. So this is how buddy system works. It repeatedly divides it into half each time until it allocates a suitable size dot to that process. Then when the pair becomes unallocated again, they combine back and create a bigger size again. Okay. So what reallocation, as we discussed in our previous video, was like when the compaction was performed. We discussed compaction in this video. Relocation was the topic of the previous video. So relocation was the addresses need to be maintained, as the program can be anywhere in the memory and there are internal references between the program. So when the compaction is done, you can say that the physical storage space at which something is stored is also shifted. Okay, because the whole memory is shifted. So the data reference between two, let's say, variables, okay, or locations or jump sequences, anything, they also need to be managed as per the new physical memory. Okay. So in our programs, we don't manage that. We just simply refers to jump to this label, and so the label actually has some physical memory, and so we performed compaction. Now the physical memory of the label is somewhere else than it was before. So the OS manages that, so we don't alter our programs. The OS manages behind the curtains and performs compaction and various other tasks and shifting those. So as we have seen addresses, so there are types of addresses. The first is logical address. Okay, what logical address is refers to some memory location independent of what is the where it is currently assigned. Like I don't care where it is in the physical memory. I just write some location that is data reference or something in my program. I don't care where it is in the physical memory. Relative address is in relation to some other logical address. As I say, like there is an array and there is a label and there is another one which refers which is based on the previous location. Okay, like plus 10 to some location, and which is again a logical address as logical address, and logical address plus something to that is again logical address, but it is relative to the first of it. So yeah, relative address is also logical address. Okay, now we come to the physical address, which is an actual location in the memory, that is which actually get assigned to some place. Okay, to actually assigned to some cell of the memory. So as we all talked about that the relative addresses are loaded during runtime. Okay, dynamic, they are dynamic. You can't you can't relate one address until the on which it is referenced got memory first. Okay, say we malloc some array, and so the array name gets the memory first during runtime, then the subsequent like a0, a1, a2 are the relative addresses with that of the first one a0. So they all get loaded during runtime, and all the memory references are basically relative to the origin of the program. Okay, so there needs to be some hardware mechanism to this kind of translation. So this is done using the hardware mechanism we can say used in this is known as base register, and another is bound register. Okay, the base register points to the origin of the program. Okay, where in the main memory is the origin of the program. Okay, so base register points to that, and bound register points to the ending address. Okay, the end address of the program or the space. Okay, which should not be crossed by the program. So yeah, these two are the base, the origin, and bound, the ending. Okay. So when a relative address is encountered, say there is some address, so it is calculated how like the base address points to the origin of the program, and this relative address is in with reference to that base. Okay, when we add this address to the base address, we get the actual address, that is the actual calculated desired address. Now this address we got then is checked with the bound register. If it is within the bounds that is allowed of that program, then yeah, it is given a location and it is stored and everything runs successfully. Yay. Okay, but now if it is out of bound, there is an interrupt scheme, that is an interrupt is generated, and that interrupts as programmed by the user or OS or whatever it is handled in some way. Okay, so the address is calculated by adding the relative address to that of the base address and checking it with the bound register. Now, as we have seen, both the fixed size partitioning and the variable size partitioning are both inefficient. Okay, they both have problems. Of the fixed size had internal fragmentation, and the other one has external fragmentation and many other problems. So the best technique that handles these both two, and the first technique, which is actually good to handle all this and is used in the operating systems, is the paging technique, and we are going to discuss it in our next video. So if you like my if you like this video, please press the thumbs up button, and you or comment down below, and don't forget to subscribe. Thanks for watching. Keep watching.